The session this afternoon will start with a talk by Edward Witten on anomalies revisited.
Well, first of all, I want to start by thanking very much our hosts here in India for organizing this conference and giving us all the opportunity to come and visit this great country again. And as you've just heard, my talk is on the subject of anomalies revisited. And I'm going to start with this question. In string perturbation theory, how does one decide if a given string theory compactification is modular invariant? Well, I want to narrow the question to the case that the anomalies of interest all involve fermions, maybe fermions possibly coupled to a sigma model, because I'm interested in questions that have analogs in higher dimension for fermions that live on branes, for instance, or for other applications of quantum field theory. So although there are a lot of things you can do that are special to 2 dimensions involving rational conformal field theory, we won't discuss them. We'll only discuss questions involving fermions that are more general. Now, there's a standard answer to the question, how do you decide if the theory is modular invariant? The standard answer is, you calculate the partition function and check whether it's modular invariant. So we work on a Riemann surface of genus 1, defined by a Taylor parameter in the upper half plane, and the definition of whether the theory is modular invariant is whether it is invariant under modular transformations. So you can certainly answer the question, is the theory modular invariant, by calculating z of tau and just checking whether it's modular invariant. So I'm pretty sure that's the answer most people would give, and it's certainly correct as far as it goes. But this answer has a few drawbacks. So for one thing, we might not be able to calculate the complete partition function, especially in higher genus or in higher dimension, or if the fermions are part of a sigma model. Even if we can, computing the complete z of tau might be very complicated, and one might wonder if the anomaly in modular invariance, which is something simple, can be computed directly rather than first computing the complete function. Shouldn't it be easier to decide if a theory is anomalous than to solve the theory? Beyond this, there's something a little misleading about the standard answer. The standard answer saying compute the partition function and check if it's modular invariant is fine if you can compute the partition function. And in genus 1 we can because there's a Hamiltonian formulation. So on a Riemann surface of genus 1, the partition function is a trace in a Hilbert space of physical states. And that gives a definition of the partition function. So the standard recipe makes sense in genus 1 when combined with this definition of z of tau. You calculate z of tau and check whether it's modular invariant. But in higher genus or in higher dimensions, there's no standard and well-known recipe to calculate the path integral. I'll clarify this in a second. But basically, in the case of chiral fermions, it's not clear how to define the phase of the fermion measure. So we customarily call the fermion path integral a determinant or a Pfaffian, but this is a term of art. If you think a determinant is a regularized product of eigenvalues, then the path integral for chiral fermions is not a determinant. That's because the fermion eigenvalue problem only makes sense if both chiralities of fermion are present, since d/ reverses the fermion chirality. So in the more interesting theories of fermions, you can define the absolute value of the fermion path integral as a product of eigenvalues, but not z itself. So thinking that the fermion path integral is a regularized determinant won't work in either the standard model of particle physics or the worldsheet theory of string theory, or most of the Brane world volume theories on branes, or lots of things that condensed matter physicists do nowadays. So if the fermion path integral is not a determinant in the naive sense, then what is it? What do we mean by the fermion path integral? So giving the best simple answer I can to this question is the purpose of the lecture. But anyway, let's start with the best answer that's well known, and then we'll give the best answer we can. The best answer Before I do that, though, I want to say the following. In some particular cases, there are ad hoc answers to the sort of questions I'll be discussing. So, for instance, and there won't be time to analyze all the ad hoc answers and see how far we would get with them. I will explain a general answer, and I won't analyze all the ad hoc answers that would give partial answers. But I'll just, as one example, say that in 2 dimensions, topology is so simple that one could normalize the higher genus amplitude using factorization, and that's the answer most people would give, I think, if given any answer about to the question, what is the meaning of the Fermion worldsheet path integral in higher genus? Now, although there's no standard method to define a Fermion path integral in general, there is a standard method to compute what happens to it when one varies some background field, which might be the metric tensor or the gauge fields that the fermions are coupled to. For brevity, I will mostly not mention the gauge fields and speak as if there's only a metric tensor, but gauge fields would be treated in the same way. We consider fermions on some D manifold M, which could be the string worldsheet in the example I started with. The response of, I write z psi for the Fermion path integral, and the response of z psi to a change in the metric is given by a standard formula that the variation with respect to the metric of log of z psi is the expectation value of the stress tensor. Now, the right-hand side is meaningful according to standard textbook recipes. It's well defined because, for example, it can be computed from Feynman diagrams. You need to regularize a little bit, but a regularized version of the right-hand side is well defined. So, although there's actually no textbook recipe for z psi, there is a textbook recipe for the expectation value of the stress tensor. That's because there's no subtlety in the normalization. So very concretely, in perturbation theory, you would calculate the one-point function of the stress tensor from summing Feynman diagrams, and there would be no ambiguous phases in the Feynman rules. Whereas for z psi itself, the phase of the Fermion measure would be unclear. Now, there is a possible problem, which is that the one-point function of the stress tensor might be affected by perturbative anomalies. We'd like the Fermion path integral to be invariant under diffeomorphisms, well, ultimately all diffeomorphisms, but at least under infinitesimal diffeomorphisms, where you shift the worldsheet coordinates by some infinitesimal vector field v mu. The condition for this to be true is that the stress tensor should be conserved in the sense that the divergence of the one-point function of the stress tensor is 0. In some theories, the regularized T mu nu does not have that property. And then you say that such theories have perturbative gravitational anomalies, and we discard them. So we will only study more subtle questions like modular invariance if the perturbative anomalies cancel, after possibly combining together the contributions of a variety of different Bose and Fermi fields. If perturbative anomalies are absent, what might still go wrong? Well, once we have a satisfactory definition of the one-point function, the formula defines z psi as a function of the metric up to an overall phase. There is an overall phase because we only know the derivative of log z, and knowing the derivative of log z leaves an unknown constant in log z and therefore an unknown multiplicative factor in z. So the indeterminacy looks like this with a constant alpha, and alpha is real because, remember, the absolute value of z psi could be defined as a determinant. Now, there can indeed be a problem in this overall phase. The condition that the stress tensor is conserved ensures that z psi is invariant under small diffeomorphisms, but it may not be invariant under big diffeomorphisms. For example, consider in the case of perturbative string theory a 2 torus parameterized by periodic variables x and y. So an example of a big diffeomorphism maps x and y to x plus y and y, and it corresponds to a modular transformation. If sigma has a complex structure defined by saying that x plus tau y is holomorphic, then phi maps tau to tau plus 1. So the modular transformation tau going to tau plus 1, and similarly other modular transformations come from big diffeomorphisms. And modular invariance is the question of whether Z psi is invariant under big diffeomorphisms, such as phi. We describe non-invariance by saying there is a global anomaly. To decide if Z psi is invariant under a big diffeomorphism phi amounts to the following. Let G be some metric on M, and suppose phi transforms G to G phi. I write G super phi as whatever G transforms into under phi. So we'd like to know whether Z psi equals Z psi evaluated at G equals Z psi evaluated at G phi. In general, this might be wrong, but it will always be true that d by dg of log Z psi is the same at G or at G phi. That's because the left and right-hand sides are both given by the one-point function of the stress tensor, and textbook recipes show that the one-point function of the stress tensor is invariant under all diffeomorphisms, big or small. Actually, that's true even when there are gravitational anomalies in perturbation theory. So it follows that Z psi changes only by a phase under the big diffeomorphism. And the phase is a constant independent of the metric, because d by dg of log Z was invariant under phi. So the fact that alpha does not depend on the metric means it's a topological invariant. And so the failure of modular invariance or any other global anomaly is measured by a topological invariant. Well, if alpha is a topological invariant, what's it an invariant of? Well, from what I've said, there's a clear answer. One answer is that alpha is an invariant of the equivalence class of the big diffeomorphism phi modulo the little diffeomorphisms, under which Z psi is invariant because we're studying a theory with no perturbative anomalies. So that's an answer, but it's not the most useful answer. A more convenient answer is this. If we're studying fermions on a D manifold M, we use phi as gluing data to build a D plus 1 manifold Y. We do it in the following way. First, we interpolate between the old metric G and the new one G phi by a one-parameter family of metrics, where a parameter U varies from 0 to 1, and I've just written a formula that agrees with G if U is 0, and with G phi if U is 1. So, by the way, concretely, to decide if there's a global anomaly, we continuously follow Z psi as a function of U, and we ask whether we get the same answer at U equals 0 as at U equals 1. But given a one-parameter family of D metrics, we define a D plus 1 metric, which is just du squared, plus a U-dependent D metric. So what I've written so far is a metric on a D plus 1 manifold, and the D plus 1 manifold is topologically just a product of M with a unit interval, but its metric is not a product because the metric in the M direction depends on U. But we're given that the two ends of the cylinder are diffeomorphism invariant under the big diffeomorphism phi. So we can glue the two ends together using the diffeomorphism. And gluing the two ends together, I had trouble drawing it, but we can imagine gluing the two ends together by diffeomorphism. And that makes a compact D plus 1 manifold Y without boundary, which is called the mapping torus. And the most useful answer to the question, what is the global anomaly a topological invariant of, is that it's a topological invariant of the mapping torus. So with this formulation of the question, I gave a formula for the global anomaly in an old paper, which I actually reported on at Santa Barbara in 1985 in what sometimes is called the First Strings Conference, although it didn't have that name at the time. The name wasn't used till 1988. The strategy was to go to a limit in which the U dependence is adiabatic and to compute using the adiabatic approximation of quantum mechanics. And the answer was as follows. I'll only state the answer very briefly. On the D plus 1 manifold Y, you consider a non-chiral Dirac operator. Since it's not chiral, it has an eigenvalue problem. And given the eigenvalues, you can define the Atiyah-Patodi-Singer eta invariant. And then I showed that the global anomaly is e to the I pi eta. So that's a general answer for the global anomaly in any fermion problem. Now, it's a general answer, but it's probably not that well known. So therefore, I'll point out that it's a slight refinement of something that probably you're more likely to know. So a relatively well-known statement is that perturbative anomalies in d dimensions are related to Chern-Simons in d plus 1 dimensions, and thereby to a characteristic class in d plus 2 dimensions. If you're familiar with that, then my statement about the global anomaly is just a slight refinement. The reason is that according to Tia, Pitoti, and Singer, eta is almost the same as Chern-Simons. They differ by a topological invariant, meaning that the variation of one equals the variation of the other. Sorry, I should have said it better the first way. So the variation of eta equals the variation of Chern-Simons, according to Tia, Pitoti, and Singer, and therefore they differ by a topological invariant, which for some purposes you wouldn't care about, but the global anomaly is a topological invariant, so there you do care about the global anomaly. And if you're interested in the global anomaly, it's important to use eta instead of Chern-Simons. But if you forget the topological invariant, you can just use Chern-Simons, and then the relation of Chern-Simons in d plus 1 dimensions to an anomaly in d dimensions is relatively well known. Now, generically, e to the I pi eta is not a topological invariant, but precisely in those theories that have no perturbative anomalies, it is a topological invariant. That's basically because of the fact that the variation of eta is the variation of Chern-Simons, and as I just told you, a relatively well-known statement is that the variation of Chern-Simons controls the perturbative anomaly. So the upshot is that a theory is free of global anomalies if and only if e to the I pi eta is 1 for every d plus 1 manifold that's a mapping torus. So that's an answer of sorts. But there's more to life than canceling anomalies. And canceling anomalies does not even suffice to prove that a theory with fermions is consistent. It's to explain the second point that I'm actually giving the talk today. The only trouble was that I realized if I started here, it would be a little bit too opaque. So I had to give the first half of the talk first. Saying that the path integral is anomaly-free means that the phase of the path integral on any given m can be defined without running into a contradiction, but it does not tell us what's the overall phase of z psi. See, alpha, the global anomaly, told us the mistake how z psi changed under a big diffeomorphism. And if alpha is 0, then with any arbitrary choice of what z psi is at one metric, we can consistently define it as a function of all metrics. But we're left with that arbitrary choice. And it turns out that that freedom of that arbitrary choice in general leads to trouble. If we pick overall phases of z psi at random for different m's, we're going to violate unitarity and gluing. We want a consistent way to define overall phases of z psi for all possible m's. And failing that, we would have to say that the theory is inconsistent. It's not hard to give examples of theories that do not have global anomalies but are apparently inconsistent because there's no consistent way to define overall phases of the path integral on different m's. The perturbative heterotic string in certain backgrounds is one example, and massless Majorana fermions in 3 dimensions lead to another example. Although I don't claim a complete proof, I believe there's a general answer for when a theory with fermions is completely consistent and anomaly-free, meaning that the path integral on a general manifold can be defined in a way that's not just free of all perturbative and global anomalies, but moreover satisfies all physical principles of unitarity, cutting, and gluing. The condition is just that e to the I pi eta is 1 for all d plus 1 manifolds, whether they are mapping tori or not. So as an example, consider the worldsheet path integral of the heterotic string. So we integrate over maps from a worldsheet sigma to a space-time S, which by mistake I called M. A space-time S. S is space-time. And what I've called M up till now, I'm now calling sigma as the string worldsheet. When you analyze global anomalies, you go to d plus 1 dimensions. So sigma is replaced by a mapping torus, which now is a 3 manifold. Because remember, to analyze global anomalies, we added an extra dimension. So in the case of the perturbative heterotic string, we go from 2 to 3 dimensions to analyze the global anomaly. And then we would compute e to the I pi eta, including contributions from all the worldsheet fields of the heterotic string. And we also have to include the Green-Schwarz mechanism, but I will omit that. The condition e to the I pi eta equals 1 has the following interpretation. So if T is the tangent bundle of spacetime and V is the gauge bundle, then the alpha prime corrected supergravity equation tells us a certain topological condition at the level of differential forms. But the condition that e to the I pi eta is 1 implies the same thing for integral cohomology. That's more than one can prove via global anomalies alone. So global anomalies would tell you more than you learn from supergravity, but less than I claim is actually true. So what goes beyond global anomalies are the extra constraints for being able to consistently define absolute phases of Fermion path integrals. The main evidence for the condition e to the I pi 8 equals 1 is what I call the Die Freed Theorem. Die and Freed stated their result in a way that sounds a little bit abstract, so when I first heard it, it sounded cute, but I didn't realize it was useful. But now I would describe the Die Freed Theorem as a useful way to define a Fermion path integral. Suppose we're trying to define a path integral for fermions on M, and suppose M is the boundary of a manifold X over which any important structures that are important in defining the original theory are extended. So here's the picture. We're studying fermions on M, but M is the boundary of X. Given this, the Fermion path integral on M can be defined as follows. The Fermion path integral on M should be defined as its absolute value. And remember, I told you at the beginning that the absolute value of the Fermion path integral is well defined by textbook recipes, times a phase, which is e to the I pi eta, but now it's eta on a manifold X with boundary. So I claim that this should be taken as a general definition of a Fermion path integral, or at least a definition that's much more general than any textbook definition. The basic justification for this formula is that it's gauge invariant and consistent with unitarity and factorization, and it satisfies the condition it's supposed to satisfy. So what more do you want in life? That's the definition of the Fermion path integral that has all the properties you'd want it to have. But we should ask whether the choice of X matters. Because if the choice of X matters, that means that this definition does not give us a satisfactory answer. So if we have two choices of X, X1 and X2, we glue X1 to minus X2 to make a D plus 1 manifold Y. The minus sign means we reverse the orientation of X2 to glue it smoothly onto X1. And then there's a gluing formula that was basically part of the Die Freed paper that compares eta of X1 to eta of X2, and they differ by a factor which is eta of a manifold without boundary. For our definition of the Fermion path integral to be well defined, we want e to the I pi eta of X1 to equal e to the I pi eta of X2, and you can see that the condition for this is that e to the I pi eta of Y is 1 for any D plus 1 manifold without boundary. So under this condition, we get a completely satisfactory definition of the Fermion path integral that obeys all the properties you'd want it to obey. But the condition you need is that e to the I pi eta is 1 for all D plus 1 manifolds, while canceling global anomalies, or avoiding global anomalies, means the same condition only for a certain restricted class of D plus 1 manifolds. So that's the general answer when a definition of the Fermion path integral based on the Die Freed theorem makes sense. you want e to the I pi 8 equals 1 for any closed manifold with no restriction to mapping tori. Well, what if there is no suitable x? When that happens, the Die Freed theorem doesn't give a complete answer, but I claim that it gives as complete an answer as there should be in the following sense. I won't try to be general. I'll give an example. Suppose we're in dimension 2, so M is a 2 manifold, but let M have an odd spin structure. Then it's not a boundary, but 2 copies of M are a boundary. So the Die Freed theorem would not define Zm, but it will define Zm squared. And that's the right answer, because if you have a consistent definition of the Fermion path integral in this situation, then changing its sign whenever there's an odd spin structure gives another that's consistent with physical principles. That's more or less the reason that both type 2a and type 2b superstring theory exist. So the Die Freed theorem determines the answer as much as it can be determined. And I claim that whatever is not determined by the Die Freed theorem is really undetermined and represents a free parameter in the theory. Depending on the context, the free parameter would be called a coupling constant, or in string theory, a background field. So anyway, my claim is that the Die Freed theorem certainly gives the most general definition that's known of Fermion path integrals, and I strongly suspect it's the right answer in general. So as I've already mentioned, the perturbative heterotic string is one in which what we learn from the Die Freed theorem is more than you learn from anomalies. I actually treated it this way in an old paper, but somehow without realizing that the Die Freed theorem was the general answer for fermions. I want to give a more contemporary example, which also would lead us to consider M2 branes and other string/M3 branes, except that we won't have time. The example I want to give is actually very fashionable in condensed matter physics nowadays, where it appears in the theory of a mostly hypothetical material called a topological superconductor. So the theory is a 2-component massless Majorana fermion in 3 dimensions, coupled to gravity only. If you consider this theory on an oriented 3 manifold, its partition function is real but not necessarily positive. You can show that there's no global anomaly. And therefore, based on anomalies only, you'd think the theory is consistent. But I believe it's actually inconsistent, because e to the I pi eta is not always 1 for a general orientable 4 manifold. So there's no natural way to pick the sign of z psi of m, even though there's no anomaly in the traditional sense. But it's more interesting, since the theory is parity conserving, to formulate it on a possibly unorientable 3 manifold. In this case, you find there is a global anomaly in general. In fact, it's been computed recently by condensed matter physicists in a special case, by Ryu et al., the same Ryu of Ryu and Takayagi. Sorry, I've forgotten his co-authors at the moment. But I mentioned the paper just to underscore that what I'm telling you about is part of contemporary condensed matter. So you find, okay, they didn't use the Die Freed theorem, they just computed by hand in an example. But you find that when you try to use the Die Freed theorem, there is a dependence on x. The way condensed matter physicists interpret this is that although the massless Majorana fermion cannot exist on a bare 3 manifold, it can exist on a 3 manifold that's the boundary of a 4 manifold. So the 4 manifold would be the world volume of some material that fills a region of 3-dimensional space, and the 3 manifold would be the boundary of that material times time, the world volume of the boundary. The material that does this is a topological superconductor, which in bulk has a gap for fermionic excitations, but has gapless fermionic modes on the boundary. So there's a massless Majorana fermion on the boundary, and the gap is bulked. When we use the definition suggested by the Die Freed theorem, we should interpret the bulk factor as coming by integrating out the bulk gap modes that live on x. Now you can ask more generally, and many condensed matter physicists have asked this, if a theory of new massless Majorana fermions, all transforming the same way under parity, is consistent on a possibly unorientable 3 manifold. To answer this question from the present point of view, we need to know whether e to the I pi nu times eta is 1 for all four manifolds x. And the answer to that question is that nu should be a multiple of 16. RP4 is an example of a four manifold where e to the I pi eta is e to the 2 pi I over 16. So to get 1, you need to take the 16th power of e to the I pi eta. In other words, the number of massless Majorana fermions should be a multiple of 16. The number 16 has been discovered and explained from many points of view in the condensed matter literature. And I don't quite have time to explain how the condensed matter physicists pose the question, although I've stated it here. Well, very briefly, they ask whether if you have new massless Majoran fermions and you add some possibly irrelevant but strong couplings, can you cause the boundary theory to be gapped? And they show that's only possible, or argue at least, that that's only possible if nu is a multiple of 16. I should also give a reference to the first paper where the role of eta was suggested. So this is a case in which anomalies do not capture the full picture. An anomalies-only approach would tell us that the theory is consistent if nu is a multiple of 8, but the correct answer is 16. How much time do I have? 2 minutes? Actually, the case nu equals 8 arises in an example that's important for string theorists, because an M2 Brane world volume is a 3 manifold, and it has 8 Majorana fermions living on it. And there are 8 which are actually coupled to a rank 8 vector bundle involving the spinors of the normal bundle to M in 11 dimensions. So the special case of nu equals 8 is important in M theory. And since 8 is not a multiple of 16, the theory is inconsistent by itself. It has an anomaly involving the normal bundle, although the anomaly is not the full story. I treated, assuming M is orientable and considering anomalies only, I treated this case in an old paper. And in that case, the answer is that something funny happens to this 3-form field C, such that that factor has an anomaly that cancels the anomaly in the first factor. But first of all, my methods were only adequate to treat orientable 3 manifolds. And secondly, it's now clear that an anomalies-only approach doesn't give the full story. So, okay, I'm not, given the time, I won't explain here what I did in the old paper. And I'll just say that to treat the general case of an unorientable manifold needs a more powerful approach than an anomalies-only approach, such as an approach using the Die Freed Theorem. And it can be treated in a way similarly to what one needs to treat the topological superconductor with nu equals 8. The M2 Brane problem is more complicated because of the coupling to the normal bundle. Now, what got me to look at this subject again wasn't what I've just told you about. I originally started worrying about a case that hasn't been treated in the literature, even at the case of anomalies only. That's the case of an M2 Brane that ends on an M5 Brane. So the M2 world volume anomalies, even if the M2 world volume is orientable, and even if you only treat anomalies and don't try to give an absolute definition of the path integral, is a very subtle problem because there are anomalies everywhere. The world volume path integral of the fermions, the coupling to the C field, and also there's this funny 2-form of self-dual curvature on the M5 Brane. So even an anomalies-only approach to that problem is rather tricky. But I believe it's hard to analyze this problem effectively without something like the Die Freed Theorem. But there isn't time to explain that. Instead, I'll have fun by ending with the following question. What would be a condensed matter analog of the M2, M5 problem? So remember, the key thing about the M2, M5 problem is that you have a 3-manifold with boundary, and there are fermions that live on the 3-manifold, but they're inconsistent by themselves. They're only consistent because of anomaly inflow from the 4-manifold. But the 3-manifold self has a boundary, which is going to make anomaly inflow from the 4-manifold, which in string theory would be the M3 would be the 11-manifold, more complicated. Well, anyway, how could you realize this in condensed matter? Well, not only you can, but condensed matter physicists do. So a partial analog, at least, would be a topological superconductor in 3+1 dimensions, whose boundary is divided in 2 parts with 2 different boundary conditions. How could you divide the boundary of so you have a solid piece of lead, but you want the boundary conditions to be different on two parts of the boundary? How do you do that in the real world? Well, you let one part of the boundary be exposed to the vacuum, while the other part is in contact with some other material, maybe copper or something. So the boundary condition on one part is supposed to be the free fermion boundary condition we discussed before, and the boundary condition on the other part is supposed to be a gapped symmetry-preserving boundary condition, only possible because of interaction, so that that part of the boundary is gapped. So I've drawn this fancifully if you're interested in the real world. Well, there's a limit to the topologies you could achieve in the real world. You can't really achieve four-dimensional topology, unfortunately, but if you want to enough, you can achieve real-world materials with a funny three-dimensional, well, at least embedded in an interesting way in 3 dimensions. So anyway, X is the bulk material. Its boundary is divided into two parts with two different boundary conditions. The massless fermions live on one part, and that would be a partial condensed matter analog of the M2, M5 Brane system. So I hope I've succeeded today, at least in giving an overview of the tools that are needed to treat fermion path integrals more carefully than is usually done. I haven't explained any specific problem in detail, which would really require a different lecture, but write-ups of some of the problems I've mentioned will appear soon. Thank you.
So I actually had two questions. One was, so you certainly have presented a necessary condition.
Yes.
And you believe it's sufficient.
I believe it's sufficient, but I don't claim to have a complete proof.
Second of all, it sounded like, so what do you take of the attempts of some of these condensed matter physicists using 16 to derive guts?
Well,
or,
well, there's the following question. Can you make a lattice theory which gives a lattice regularization of the standard model? There's a reasonable scenario for doing that, I would say, using the fact that well, it's a variant of the fact I stated in the lecture, but a similar fact. I would say that there's a reasonable scenario to do that, and it's been done reasonably convincingly in 1+1 dimensions for analog. I don't think it's really been done in 3+1. It's more that a philosophy about how to do it has been explained, and the philosophy is reasonably convincing.
Based on the same kind of argument you were making,
yes.
that it's only possible for restricted guts.
No. I claim that that's not true. I claim that this story with e to the I pi eta gives a general answer for what theories are consistent. And I believe that it's very likely that the condensed matter physicists making that claim are not completely correct. But their story about giving a lattice regularization of the standard model makes perfect sense.
But, so going beyond that, are you willing to say anything about whether that restricts the guts that we could?
I do not believe that this story with e to the I pi eta gives any restriction on guts that's not previously known. I've thought about it several times, and I've always reached that conclusion. And because the conclusion is negative, I've never written it up.
Other questions? We probably ought to go on to the next talk, since we're a bit over time.